Hello, my name is Gerline Dillon and I'm recording this on Monday, April 4th, 2022.
For my schematic, as you can see above, I decided to use a BJT transistor because this circuit requires a higher GM that a MOSFET can simply not provide. The amplifier topology I decided to use was a common collector because a common collector has a good behavior as an output stage and it meets the input signal swing requirements. To determine the values of certain variables, many calculations had to be completed. I first started off by solving for Gm by using the equation V internal is equal to 0.2 multiplied by V thermal, which is multiplied by 1 plus RL times Gm. And after rearranging and subbing in the values of 25 millivolts for V thermal, 0.5 volts for V internal, and 100 ohms for the resistance at the load, I could solve for Gm to be about 0.99 S or 990 ms. Now that I have my Gm value, I can use it to calculate the internal resistance, which I use the equation which was posted in Project 3 design guide. This equation was Gm multiplied by RL divided by 1 plus Gm multiplied by RL, which is then multiplied by Rin divided by 100 plus Rin. And this should be bigger than or equal to 0.9 because we can only have a 10% attenuation. After doing the calculations for Gm and determining it was 990 ms, and knowing the resistance at the load was equal to 100 ohms, we could rearrange the equation I had just stated previously to solve for the internal resistance, which I determined to be equal to or larger than 1000 ohms. To create this schematic, I referenced the Project 3 design guide, in which there were examples of how to create this type of schematic, and I simply followed its main guidelines for the components and added my capacitors as I deemed fit to make sure I could get the correct input and output values that we needed. To model this transistor in LT-Spice, I used a built-in LT-Spice model for 2N3904. I followed a similar design to the one posted under the Project 3 design module, except I added another capacitor in parallel with RL on the emitter to determine the voltage output, which when graphed, you can tell that the output has almost the same values as the input voltage. They are only slightly off. To determine the gain, the formula which was used earlier on in the calculations was used again, except this time it was rearranged so that the simulation results would graph the gain along with the input and output values. The gain that was determined from this simulation was very close to 1, which matches the calculations which were done previously. For this simulation, I used the sine and AC functions for the input voltage to represent the sine wave and the small signal AC analysis. To run this simulation, I used the transient simulation command to run the simulation. From this simulation, I was also able to determine that the voltage input is only slightly higher than the voltage output, which means that the voltage output will fall in the less than 10% attenuation range. From this, you can also see that the voltage input and the voltage output are both at around 0.5 volts in amplitude, which means that the circuit was able to accomplish the goal of only having an input of 0.5 volts. To determine the gain results in this simulation, I reused the same equation we had done to complete the calculations in earlier steps, but it was only as a reference point. To actually do the gain calculations for while we compare the amplitude of the output divided by the amplitude of the input, you can do those measurements by looking at the points on this graph and comparing it to the values given by the gain equation typed up in red above. For example, you can look at the peaks of both the output and the input. If you were to divide both of them by one another, you would get 1, which is the peak of the gain function written above. In my circuit, the BJT is placed exactly in the center right here. From there, the collector, which is right here on this side, is connected straight to this positive line, which will all end up merging together and go into positive 5 volts. The negative line on the other side will all gather together and go to negative 5 volts. So on the collector end, it goes from here all the way to the positive 5 volts. The emitter node has 2 outputs. One of them is connected to this capacitor right here, which is 104, so 100 NF, and that is connected to this wire right here, which goes all the way to 2+. This is supposed to represent our V output so that we can measure it later. On the other end of this emitter, we have this resistor, which is 100 ohms, and it's supposed to be our RL. It goes all the way to this end over here, which is then connected to our negative 5 volts as mentioned earlier. Lastly, the base of the BJT is connected to this red wire, which is then moved over to this side over here. From this red wire, where there's much more space, you can see that there's 2 100K resistors. Both of them each go to a positive 5 volts and a negative 5 volts that was mentioned earlier, which is also shown on my schematic. After that, you can see that one last node is connected to the base, and it is this 104, which is 100 NF capacitor, is connected over here. This is then connected to this resistor, which is 100 ohms, and that is our RS. It goes all the way following this purple wire to this end right here, and then it is also connected to these 2 wires right here. This white wire follows all the way to W1, and the other gray wire follows all the way to 1+. All of these connections that were made earlier, so the 1+ and the 2+, which are each connected to V in and V out, which are right here, as well as the voltage positive, voltage negative, which are connected over there, and the waveform over here, are all put together so that we can make the simulation on waveforms. In the next simulation I did, which was the waveform measurements, I decided to plot channel 1 and channel 2. The 1+, which was for channel 1, was connected to the input of input voltage, and the 2+, which is connected to channel 2, was connected to the output voltage. This was done so that we could easily graph them on waveform and compare what they look like under this waveform. This was done as an extra simulation to confirm whether the output and the input had almost the exact same values. And as you can see from just looking at this graph, you can tell that the values were very close to one another. If we take it one step further and look at the values which are displayed on the screen and do the math, you can confirm that there is a difference of less than 0.9, which means that there is less than a 10% attenuation in the voltages. Using waveforms, you can also look and compare the amplitudes of both of the channels. As you can see in the measurements column, you can tell that both of the amplitudes of the measurements are all very close to 500 millivolts, which is the required amount for both of the input and output voltages. You can also tell that the phase difference is very low, which means that they are within the 10% attenuation. To set up this simulation, I also used WaveGen and supplies. WaveGen was used to set up the amplitude of the wave, and the supplies was used to set the voltages of the top and the bottom volts. So they would give in a positive supply of 5 volts, and it would also give in a negative supply of negative 5 volts. Another thing I chose to measure was the XY graph. This was used so that to check the linearity at the input amplitude of 0.5 volts. As you can see above, the line that is formed on the XY graph is not a very straight and thin line, which means that it is not extremely linear, but it is not a very thick circle-like shape either. It's a very thin oval, which means that it is almost linear at an amplitude of 0.5 volts. From the amplitudes you can check in this waveform graph generated, you can tell that the gain that was determined was almost the exact same as the gain that was determined on LTSpice as well as in the calculations, which means that they were almost 0.99 or 1 S. Or you could say that they were about 990 ms.